Now, before we go into the next section, I need to talk about orders of magnitude. And so you will often see a symbol that looks something like the following. It's an O followed by X, or O followed by a 1, or O followed by a delta, whatever it is. These things are simply saying what is the term on the order of a magnitude. So if I have ax plus b squared x plus c cubed x. Okay. This is my equation. Currently you have no idea, how this equation is going to really resolve. We don't know what A, B, or C are. But if I were told you that A was 10, okay, and B was 0.1 and C was equal to 0.01, you would quickly realize this function right here is a function of x. Well, that function of x is going to be more or less the same as just saying ax, because the b term is tiny and the c term is just minuscule. They don't do anything, okay? So this one right here is on the order of, we can more or less just say 0, and this one is also on the order of 0. So they're tiny. They're not doing anything. I can cancel them out. I can still do a really good approximation here without having to worry about the full form. So that is important for us, because when we start talking about our boundary layer equations, I can deal with them. I can deal with them in their full form, but there are ways that I can simplify them to make them easier to deal with, okay? Easier to deal with. So let's go ahead and get into that. I'll give you the boundary layer equations first. Why? Because why not? And then we will go through how we got there. So you can just take the equations and run with them if you want, but otherwise, let's deal with this. So we still got our basic equations: continuity, momentum, and energy. So we'll do continuity first. These are my boundary layer equations. And then we'll dive into why they look like this, because these are all coming from the full Navier-Stokes. Okay, the same equations we use to build everything else, we're using here for our boundary layer. Okay, so first off, continuity. There we go. And that'll be del of rho u del y plus del rho v. Do my best to show that as a v. I, of course, failed already. That's an x there. That's an x. Del y. There we go. Is equal to 0. Nothing too crazy there. X momentum. You're going to be like, do we simplify this? Not really. No. I mean, some simplifications, but it's not much. So when we get to y momentum, that we really see the simplifications. This is going to be rho u du dx plus rho v du dy is equal to negative dp dx plus d dy of viscosity times d dy. Oh, sorry, du dy. I gotta do a better job of writing this out. Okay, some simplifications there if we actually look at the full Navier-Stokes. But y momentum, this is where it gets glorious. dp dy equals 0. Nice! I like it. There's no pressure gradient in the y direction. At least we're assuming there's no pressure gradient. And for the energy equation, well, I'll give it to you. We're not going to do too much with it here, but I'll give it to you just because. That's going to be rho u dh dx plus rho v. Change the enthalpy with the y direction. is equal to my gradient in the y direction of k dt dy plus any sort of pressure contributions and then finally viscosity times du dy squared. Okay, we've got continuity, we've got x momentum, y momentum, and energy. Where did these come from? That is what we're going to jump into next. Okay, that's what we're going to jump into next and be able to solve and figure out why we have them in this form.